dynamics of optimization, is a theoretician working on active fluids and and phase separations. Like he'll take over from Will, who did equilibrium stuff, and he'll drive out flow.
Well, thank you, Angela, for the introduction, and thank you for inviting me. Before I go into the actual topic of chemically active droplets, I want to get one important message across, and that is that this is actually an awesome school. I myself was a student here in 2011, so many years ago. Here's me, and here's actually Angela. So we met first in this school. And surprisingly, many of those are still colleagues of mine, and I have very good connections with them. And we had a lot of fun during the school, so I want to share some pictures, which have apparently quite bad quality because the photograph at this time was not that good. This was 4th of July. This is us on a hike. This is us whitewater rafting. I have no pictures from the lectures, apparently. So, well, I guess priorities, but and here's another hike. I guess the point is that besides these awesome lectures, there's a lot of fun, and you should really engage with each other and learn from each other. Okay, that was my 1-minute pitch that this is really awesome to be here. And as Angela already said, that rest of the time I'm going to spend on phase separation, and in the theme of this week, I'm going to go to non-equilibrium system, to actually active matter in a broader sense than Christina introduced in the in her talk and in her lecture before lunch. So I'm generally interested in phase separation on both soft matter systems and also biology. You heard about this last week from Will Jacobs. So when you think of droplets, I mean, you have probably something like this in mind. This is exactly the picture I have in mind too. You will see that I work not on a molecular scale, but on a coarse-grained scale. So some droplets. Now, why am I interested in that? Again, the motivation comes mostly from biology. I'm sure Will told you all about this, that these droplets actually are very important to organize biomolecules in space and time in cells. And this is a picture he might have even have shown because it's from a very important review in the field, basically showing that structures like these come up in all kinds of cells and are involved in all kinds of processes. I'm not going to go into the biological details because I think that's not so important here, but it's clear that by self-organizing molecules into droplets, you can organize where these molecules are. That's the basic message. And that is basically another layer of organization, spatial temporal organization, beyond these membrane-bound organelles like the nucleus and so on. And I think the picture that emerges in biology now is that there is a hierarchy of organizations. All these processes play into each other. And that makes it very complex, but also very interesting from a physical point of view. That's what we study. More specifically, I'm not so surprised that these droplets form. I mean, you heard from Will last week that basically once you have interactions in a multi-component fluid, you will have phase separation. And there are more precise statements in these papers down here, which really go into the physics of multi-component phase separation. Our group works on this a little bit too, but I don't have time to go into the details here. But I guess for a physics audience, it shouldn't be surprising that if you have many different particles that are bound to interact, you mix them together in a closed system, that then the homogeneous state is not the free energy minimum. Got to basically, with overwhelming probability, you'll find some phase separated states. So in that sense, actually surprising that biology stumbled upon those only like 15 years ago. Although, little historical side note, about 100 years ago, before we even knew about DNA, people were suspecting that actually the cytosol undergoes phase separation. But that was then lost, apparently. So taking my physicist hat, I'm basically saying, well, it's pretty likely that these structures are there. It also makes sense to use them in cellular processes because you need to arrange molecules in space and time. But in order to do this effectively and be responsive to external stimuli, cells need to be able to control when these droplets form, where they form, how large they get, and so on. And this is really the question we are after in my group on the theoretical side. We'd like to understand how cells control these droplets, which, by the way, are often called biomolecular condensates. And a bit of history of the terminology. So when we speak about droplets, we often think about liquid-like things, right? Like oil droplets in water, for instance, or just water droplets on a windshield. Whereas many of these droplets in cells actually possess solid-like properties, or viscoelastic, as Noah introduced in the first lecture today. So they are complex materials. We're only beginning to understand how this is regulated, how this comes about. But they're certainly not always liquid-like, and that's why they're often now called condensates, simply stating that they form by condensing material into a lower space. All right, so I'm looking for physical processes that can be used by cells in principle to regulate these droplets. And then we work basically in two different directions. On the one hand, we do fundamental models where we basically combine the physics of phase separation that you heard last week about with other physical processes, for instance, elasticity theory or chemical reactions, which is what I want to focus on today. This is like the pure theory side of our work. But on the other hand, we also collaborate with biologists and literally look at particular systems and try to figure out what's going on. And so there's a back and forth between these two, and I find it very stimulating. Now, when I think about regulation of such structures and also just regulation in general in cells, I think what quickly comes to mind is that cells, of course, can make proteins and they can destroy proteins. And clearly that will also have an impact on phase separation, right? If the material is not there that wants to phase separate, it can't phase separate, so you don't have a droplet. So by controlling how much of a particular protein there is in the cell can certainly control whether this particular condensate like one of those forms. But this is a really pretty slow response because it takes a while to make proteins and to degrade them. And it's also pretty costly, right? If you want to, because you need to take the whole machinery into account. Now, an alternative way to control things in cells, very generically, is to modify the molecules you already have. And this is a huge field, which can be summarized as post-translational modification. Basically, what it's saying is that once a protein is made in a cell, you can modify it by adding chemical groups. And here's a list from actually some review or some editorial from this paper of many different chemical modifications that are commonly found in cells. You might have heard about phosphorylation, methylation, ubiquitination, and so on and so forth. Many of those I have never heard before. I can't pronounce them, so I don't think it matters. All I'm saying is that the cell has a huge toolbox of how to actually modify proteins after they have been made. So it's not like that a single protein exists from like its birth to it's actually degraded, but it's modified in between quite a lot. And you can imagine that there's a combinatorially large space of modifications because you can do these modifications in different parts of the protein, combine them, and so on. So I think a better way as a physicist to think about proteins is actually that there's a collection of different states each protein can be in. Okay, but for us, I mean, I'm a physicist. I can't, as I said, pronounce these things. I don't know all the protein names. I don't want to go into all the details. We shouldn't really be worried about this. What I'm going to do is try to convince you that also the simplest model already gives us interesting effects. So I'm simply going to say that my generic protein, which I'm not going to name, has two states, which is the lowest number of states where interesting things happen, of course. And I simply call these states A and B, because these are the first two letters of the alphabet. And the key idea that I want to convince you of is actually useful to think about in the next 3 lectures is that a chemical transition between two different states of the molecule can have an effect on phase separation. And the idea is that the cell can then use modifications like these to control whether droplets form, where they form, how large they get. So this is the entire goal for the lectures. And now we just need to fill in the details, I guess. If you want to think about this on a very conceptual, qualitative level, you can convince yourself that this is a useful framework by going to the extreme case where one of these states, in this case the A state, is soluble in the surrounding solvent. So I'm picturing a simple system where you have some solvent, be it water or whatever, it doesn't really matter. And I have a protein which is soluble, and then you just get by diffusion a well-mixed system, no interactions. Basically, you can think of this as an ideal solution. This is when all the proteins would be in the A state. And now I simply say that there's a different state. I'm not going to specify the molecular details. They're not really important here. But I say that in this different state, somehow the molecules are interacting differently, be it because they attract each other or they repel the solvent. And so they want to phase separate. And you learned all about this from Will's lecture last week. So basically, the idea is that I have a phase separating form B, which wants to form droplets. But this phase separating form on molecular level can transition to a soluble form A, which doesn't want to phase separate. And then you can imagine if I swap the chemical equilibrium, if I can somehow shift whether I have more B or more A, I can control whether I will have a droplet in the cell or not. This is extremely qualitatively, and I will show you in the next lectures that there's much more to it, much more details. And to show this, we actually will go into, we need to go into the thermodynamics a little bit more, because I want to convince you that the thermodynamics of chemical transitions and phase separation are strongly coupled. One cannot discuss them in isolation. And also, we will see that to get interesting effects, we will need to drive the system out of equilibrium. So we need an energy source and all this. And that's, of course, in the spirit of this week, where we have active systems. So the plan roughly is that we combine three things. We have phase separation to make these little droplets. We have chemical reactions to have this key theme that you have two different species. And we have non-equilibrium. So that's really the idea. So something phase separates, something reacts, and something is driven out of equilibrium. And I would claim that such system on this qualitative level, again, can also be categorized as active matter, but it's a different kind of active matter than what Christina introduced before lunch. Because clearly, when we have these chemical transitions, we use energy on a local scale. So it's a locally driven system. But there's no self-propulsion. There's no directed motion in the system. So just to give you a bit of, and this is a discussion which is ongoing in the field, and I think it's useful to introduce some terminology to distinguish these two kinds of active matter. And I think I would call what we discussed before lunch, motile active matter. And this, for some reason, which will become clearer later, I would call growing active matter. But that's just terminology. Yes?
What unifies them as, why do we talk about active matter?
So my personal subjective view is that active matter is matter which uses energy on a local scale. And that's in contrast to driven systems like hydrodynamics, where you drive on the global scale, on a system size scale. This is how I use the terminology, but I'm not sure the field has converged on a definition. Good. By the way, I'm happy to be interrupted at any time. I mean, I can skip things at the end. That's fine. Good. You can, I mean, you can work, yes, that's on the global scale, but even locally on each individual molecule, when you switch it to have another interaction with its neighbors, you might need to induce work there already against the interactions of the surrounding molecules. Yeah, exactly. So it's still converting chemical energy locally into work, but it's a different kind of work than self-propulsion. Yeah, that doesn't make any sense at this point in the lecture. I'm not sure this is the best term. I didn't come up with it in my defense, but if you have suggestions for a better term, I'm also happy to adopt it. I mean, I think it's really a discussion in the field on how we should best call these things. Everybody can contribute to count. Yes, Julia. The system I'm talking about. So the question was whether these systems are always driven out of equilibrium or whether they can relax back to equilibrium, if I understood correctly. And I think both. I completely agree, yes. You can also have non-equilibrium systems which are simply prepared in an initial state which is not compatible with equilibrium, and then you get a non-equilibrium transient which goes to equilibrium. That's not active matter. The systems I will discuss not today, but probably later this week, yes. They're continuously driven out of equilibrium. And that's key for the interesting properties. Otherwise, it's just a boring equilibrium system, which is obviously what I want to start with first to set the ground. Any other questions on terminology or other aspects? Good. Let's go to the plan for the lecture. So I talked to Will, and he apparently introduced all the equilibrium aspects of phase separation, and I will build on that. But he didn't tell you much about kinetics. And Christina Marchetti actually told a little bit about this in the end. I'm going to basically start right off where she left and talk to you about the kinetics of phase separation. That's the first part. And then I stressed already that we need to also worry about the chemical reactions, and particularly the thermodynamics. So this will be the third part of the lecture. And then I want to combine these two, and this would be the larger part. There we get the interesting things. Good. That's the plan for the next 3 lectures. Okay. One more point about motivation. I want to really convince you that it's that the chemical reactions and phase separation are linked by their thermodynamics, and we can't simply write this like an ideal diffusion equation or mass action kinetics as you might be used to, but this is a bit more complicated. And to show this, I'm just going to go through some schematics quickly. So I have this picture that I have this phase separating material B, which makes a droplet. So this is enriched in B, coexistent with dilute phase. And then if I have phase separation, and generally can quantify the concentrations of any component inside and outside by a partition coefficient, which just gives me the ratio of these concentrations. I can do this for both species. And in general, if I have phase separation, these partition coefficients will be different from 1, and they can be different for each species. That's just quantifying physics of phase separation in the simplest possible manner. Now, you might be aware if you have a chemical reaction in equilibrium. Now I'm going to look again at the conversion between A and B. I can now have this both inside and outside the droplet. And chemical reactions are governed by equilibrium constants. And these equilibrium constants are really also just the ratios of concentrations. But whereas here we had the ratio of the same species inside and outside, here we now have the ratio of different species in the respective phase. So you have an equilibrium constant inside and one outside. And that governs the chemical equilibrium. Now we can already see if I combine these, I can show quite easily that the ratio of partition coefficients must be equal to the ratio of equilibrium constants. And that's simply seeing here, right? I mean, it's very easy to show. And what this shows you is that I can't think of the phase separation isolated from the chemical reactions. These two things are coupled. And the underlying reason, as we will see, is that they are driven by the same chemical potential. So these things are linked. And this is where I want to go to the blackboard. And I hope I hit the right button. Very good. Okay, let me start on the left. So now that I could hopefully convince you that thermodynamics are important and we need to think about phase separation and chemical reactions, I want to start with the kinetics of phase separation. So basically, this will be important because when we drive the system out of equilibrium, we not only, I mean, we can no longer describe what the behavior of the system by just using equilibrium thermodynamics, but we really need to take the kinetics into account. And since this also connects nicely, oh, it's just this. Since this connects nicely to what we just discussed right prior to lunch, I thought it was good to start this. I'm going to write some equations that you've just seen. We can discuss them again. So I'm immediately going to start with what Christina Marchetti called a hydrodynamic theory. So I think about a concentration field in a closed system, and I wonder how this concentration field evolves in time. And for simplicity, we only have two components here. Let's just focus on the concentration field of this phase separating B component, because I want to know what the droplet is doing. So if I want to know how the concentration field evolves in time, in the simplest case, I have a continuity equation, exactly like we had on the board like 1.5 hours ago. And to first discuss only the physics of phase separation, so no chemical reactions for now, we can assume that this field is conserved, meaning that the particles only move in space, but they don't really get created or destroyed. And what you also already saw is that this diffusive flux, or this total flux of the material, has a diffusive component, which I write like this. So this is my mobility at capital lambda, was a capital M before lunch. I need to stick with my notation because otherwise I mess things up. And then there might be an advective term, which I will actually neglect here because I'm not interested in the hydrodynamics of this. So I'm basically thinking about a system where we don't have any hydrodynamic flows, but in principle, one could include it here. And then if you combine those two, and this is what we also had already on the board, you get what I would call a generalized diffusion equation, like so. And I'm including the mobility in here in the divergence because it can in principle depend on composition. And to show you that this is important, I want to do a quick calculation, which I can, let's do it actually on the other board. So I'll move around a little bit so that these people over here also can see them. So I quickly want to do the calculation of an ideal solution to convince you that this generalized diffusion equation actually describes interesting physics. And for an ideal solution, the chemical potential is basically proportional to kBT logarithm of C plus some constant, which is often called the reference chemical potential. And if you plug this in to this generalized diffusion equation, where the KBT is a constant, we assume isothermal system. And usually in the cells, like the heat spreads so quickly that is a good assumption. So we get this. We get the divergence operator from there. Now we have to specify the mobility. And the mobility is not easily derived from thermodynamics in contrast to the chemical potential, but it relies on actually microscopic assumptions, right? It really tells you how the molecules respond to changes in chemical potential, gradients in chemical potential in this sense. In the simplest case, the mobility is proportional to the concentration. And the idea simply is that if you have more material, you can move more around. Let's write this in here. And then we get the logarithm C. This reference chemical potential is a constant, so it doesn't really matter because we take a derivative and then it will go away. Yes? What's that? Sorry, can you speak up? You are absolutely correct. Thank you. That is actually important. Sorry. And then here too, obviously. Thank you. And the chemical potential, we had this also earlier, can be calculated from a free energy. Thank you. This is important. So we can do this calculation. Not very complicated. You take the logarithm of the derivative of logarithm, so you get 1 over c gradient of c, and then the rest just stays here. So these two c's cancel, and then you see that you get kBt times lambda times the divergence of the gradient, which is nothing but the Laplacian of c. And if you call this prefactor suggestively d, you see that we basically here have a simple diffusion equation. And that makes sense, right? Because we assumed an ideal solution, no interactions, particles obviously don't care about each other. And if we do this correctly, from this generalized diffusion equation, we just get the normal ideal diffusion. Yes? Because I mean, first of all, it depends on what system you're looking at. Like this is really system dependent and depends on the microscopics. There are two. What's that? No, the entire form. Like if you have a complicated polymer solution, then this might very well be more complicated. Like there are two arguments for why this is the simplest form that I know of. One is simply that you want in an ideal mixture, in a dilute ideal mixture, you want this equation. So by basically reverse engineering, you see that this form is the required one. And the other one is simply that if you have non-interacting particles that move around, each particle itself is basically moved by, or like feels this thermodynamic force of the gradient of the chemical potential. And the total flux is then simply proportional to the number of particles. The more particles you have, the more particles move. And that gives rise to, like if you then divide by the volume, this gives rise to this concentration dependence. But there might be arguments for why you want to have a constant. I've not heard any, but I think this is the simplest form that I'm aware of. Good. So that's nice, right? Because it means that if we plug in a chemical potential with this simplest ideal gas, then we get also what we know. And I want to repeat this later for the chemical reactions. Good. But now, of course, Will told you last week that if you want a phase separation, you need non-ideal solutions, right? You need some interaction terms here. I'm sure he told you about Flory-Huggins and so on. And there's an action parameter. And if you have that, then you can have phase separation. Right. So that's actually in the most general form that I require here, we give the total free energy integral. I'm sure this is something you've seen. There's some local part of the free energy, which you might take as Flory-Huggins or some other form. And then I hope Will also introduced you to this gradient term, which penalizes gradients and is important to stabilize interfaces. it also gives rise to surface tension. So I'm gonna be quite general here and not specify the local free energy, but if you want to have something concrete, think of Flory-Huggins. Okay, now we can take the functional derivative to calculate the chemical potential. Not going to do it in detail, but basically you get one part from this integral, which is quite easy, and the second part looks like this. If you don't know how to take functional derivatives, then just take it as granted. And if you plug this all in, our generalized diffusion equation up there, we end up with an equation which will be central to this lecture. Which looks like this. This is just inserting things, and this is something I would call a Cahn-Heod equation, which is the seminal equation that describes the dynamics or the kinetics of phase-separating systems. And you see there are some details that we need to specify if we want to actually describe a concrete system, right? We need to describe the thermodynamics, which is mostly encaptured by this local free energy density. We need to somehow say how strongly we penalize gradients, which will basically say something about surface tension. And we need to make a choice about the kinetics. Okay, now this is nice. This is a partial differential equation. We need to add boundary conditions. In the simplest case, as theoreticians, we always use periodic boundary conditions because they don't need to think so much. But one can actually also discuss a lot about boundary conditions because the material might interact with some walls and so on. But what is nice is just a simple scalar partial differential equation. You can simulate it in a computer, which favorite free energy, and can look what happens. In particular, you can ask about what happens at early times when, for instance, start with a homogeneous phase. When do droplets actually form? And you can also ask about what happens over long times when the system actually goes towards equilibrium. And these are the two limiting schemes that I actually want to discuss in detail now. Next. I'm not going to show you numerical simulations, but I actually want to calculate things. Okay, so this is a central equation, and let's maybe use this blackboard more. So I want to first discuss the early time dynamics, early stage dynamics, to get a feel for why this equation, or under what conditions this equation actually leads to phase separation. Like so far, it's a partial differential equation. I could simulate it, but we haven't really learned very much yet. And so we're going to talk about something which is called spinodal decomposition. And I will tell you what this means. All right. So you can easily convince yourself that a homogeneous state is actually a stationary state of the system. You can see this quite easily. Like by homogeneous state, I mean a field which is the same value everywhere. If you plug this in here, then this ablation doesn't contribute. This goes away immediately. This just becomes some number, right? I mean, the function evaluated at a constant value. If you take the gradient of that, it's also going to go away. That shows you that this is a stationary state which just moves in time. Yes. This K is a kappa. It's just a prefactor which tells you, like it's probably easy to see here. It's a prefactor which tells you how strongly gradients in the field contribute to the free energy. If kappa is larger, then the equilibrium solutions want to have shallower gradients. The question is about, I guess, the origin of kappa. Like if you were to coarse grain a microscopic model, indeed in the simplest situations, this kappa will be proportional to the chi parameter that you know from Flory-Huggins. So it is indeed coming from microscopic interactions. But you could also imagine more complicated models. And so I want to treat it as an independent parameter here. I think there was another question over there, but maybe not. Oh, yes. So where do you think there's a sign error?
Oh,
Okay. Yeah, please call me out on sign errors. I tend to make those. Good. Any other? Yes. FC is what I would call a local free energy density. It basically just tells you if I have a little system. So okay, what's underlying all these hydrodynamic theories is something I would call local thermodynamic equilibrium. And the way I think about it is that you have a large system, you chop it up into smaller subsystems, and each small subsystem, you can assume the system to be equilibrated. So you can define concentrations, pressures, and all of these thermodynamic variables. In particular, you can define a local free energy for each subsystem. And then you do that, but the entire system might not yet be in equilibrium. So different subsystems might have different values. And what we are concerned with here is how the large scale behavior, the long length and time scales behave. And this f of c basically captures how the free energy of each little subsystem depends on the local composition. So it includes both entropic effects and enthalpic effects, which they can describe interactions. So because the question is here, I mean, simple, if you want to have something concrete, you can think of the Flory-Huggins free energy, which one can write in various terms, but let's do it like this. Nu is the molecular volume, which we need to include here to get things dimensionally consistent. So this would be one choice, which you have hopefully seen last week. And nu is just the molecular volume, which I need to for dimensional reasons. Don't worry about it. If you think in terms of volume fractions, then these all go away, and that's what we want to do. And like nu times c is the volume fraction. And most important is this parameter chi, which is called the Flory parameter, and tells you how strong these molecules interact. This is what I would plug in here, just for, because that's something you should know. Yes.
For I like the law, right?
Yes.
Yeah, but then why would kappa be constant?
The question is why kappa would be a constant, and the general answer is that it's normally not. So in principle, kappa can depend on, or does depend on composition, but I don't want to make my life more complicated. Good. All right, let's continue. So I left off where I started with a homogeneous state, and it's quite easy to see that such a homogeneous state is a stationary state of this Connell equation. And if you did dynamical systems or complex systems, then you know that you can learn a lot about the behavior around stationary states. So what we're going to do next is actually see and analyze whether this stationary state is stable or not with respect to small perturbations. It's basically what we're gonna, where's it all? Good. So we're gonna investigate the behavior of a concentration field which is slightly perturbed around this homogeneous state. And the way I would do this is by, let's do this slightly differently. You just have a perturbation like this, which is small compared to all the other values. And one way to do the calculation is to assume that this is basically given by plane waves. If you're used to these kind of analysis, you can also think of a Fourier transform of this partial differential equation. So this is our ansatz. And we can do this because if we just have small perturbations, we can linearize the equation. And when we linearize the equation, we have the superposition principle. And then we know that this is the solution. Was the question? Yes. Yes, thank you. Yeah, I usually write these terms in terms of volume fraction, and all these factors go away, but yeah, thank you. Good. So I want to go through the calculation because I think it's helpful to see how one can actually analyze the stability of these partial differential equations. That's something that comes up all the time in in these kind of systems. So we're going to do the calculation. So the idea is to basically plug in this ansatz into our Canhil equation of this general form. I'm going to keep the free energy density general because that's where we learn the most. Left-hand side is just the time derivative. We take the time derivative of this, which just gives us the omega, which comes down from here. And this whole thing stays the same. Time derivative of the constant, of course, is values. The left-hand side was easy. I think everybody can follow here. The right-hand side is a bit more involved. So we have this divergence here, which we need to keep for now. And then there are two terms inside the divergence. There's this composition-dependent mobility, and there's the gradient of the chemical potential. So now I have a composition-dependent mobility. I'm saying that I can expand that also for small perturbations. So I get this is just a Taylor expansion. I get this for the mobility. And this is multiplied by the gradient of chemical potential. And for the F prime, like the derivative of the free energy density, I can do the same thing. I can also Taylor expand this. Then I get a second derivative times dc. And then I have the kappa term, which is just the Laplacian of c. Laplacian of a constant vanishes. So all I'm left with is Laplacian of my perturbation. Now I need to close the. So far, so good. This looks quite horrible still. It's difficult to read. But we can actually remove quite a few things. On the one hand, we know that this term is not going to contribute because C naught is a constant. Then F prime of C naught is a constant. If we take the gradient here, that's never going to matter. So we remove it immediately. And another term we can actually remove is this term. And the reason simply is that we want to only keep the terms of lowest order, the terms that are linear in the perturbation delta C. Now, if you look at this, you have this term, which, because we canceled this, is now proportional to dc. And we multiply it by this term. The first term is of order 1. The second term is of order dc2. So if you take this term times the second one, we will get terms of order delta c squared, which you want to neglect, meaning we can neglect this term altogether. That's pretty nice. So we go on from here. From this term, we only have the mobility evaluated at the stationary state concentration left. That's a constant which we can pull out. And then we have the divergence of this gradient, which again becomes a Laplace. And inside Laplace, what's left is epsilon prime delta C minus kappa. And there's a square bracket missing. This bracket I don't have it. Okay. Like so. Okay, much better already. Now, of course, we need to also apply the spatial derivatives. And since you have this ansatz for delta C, this is quite easy to do. We just differentiate it twice with respect to this term. So Laplace is just a derivative with respect to the position vector R. If we do that twice, we pull down I times Q twice. I squared is just minus. So basically what's happening, and that's a rule of thumb which applies quite often, is that the Laplace operator will be replaced by minus Q squared. This comes from this. So we get a minus sign here. This and this Laplace. So this is from the first Laplace operator. And inside, we get the same minus sign, which comes a plus sign with this, squared, and the delta C we can pull out. Now this is super nice because now we have a term on the left-hand side it says omega, which is actually the perturbation growth rate, times delta C is given by some expression times delta C. So we can cancel delta C, and this will hold for every perturbation. So what we found is omega as a function of Q, which now I'm just going to copy this. Plus kappa Q squared. And this is what's known as a dispersion relation, because it tells us how these plane waves actually evolve in time. And you might have seen that in your electrodynamics lecture. So really, if you look at this, if this omega is positive, then this perturbation is going to grow with time exponentially, at least in the linear regime, right? And that's what stability analysis tells you about. Whereas if this omega is negative, then perturbations decay in time. So basically, this perturbation, this dispersion relation tells us which perturbations will grow and which ones will shrink. Now we can sketch it quickly. There are really two cases. Can either look like this or like this. I should label my axis. You can convince yourself that the perturbation at q equals 0 is 0, right? If you plug this in, you see this. And this is directly connected to the fact that we have a conserved field. Basically says q equals 0 is a global mode, and it says that the perturbation of the global mode can't do anything. It needs to stay there. That's the conservation law. Fine. You can also convince yourself that for large q, it needs to be negative because this is a polynomial where the highest term is q to the 4, which is this. Kappa is a positive term. It needs to be positive. The mobility needs to be positive. Otherwise, we get problems with the second law of thermodynamics. So the whole term of q4 is negative and will dominate at large enough q. So all perturbations which have very large wave number, which means very small wavelength. So I should probably say that the wavelength is given by 2 pi over q. So small wavelength perturbations are all dampened. And this is exactly due to this kappa term here. Makes sense, right? Because we don't want high gradients. They give too high free energy. So these are all dampened out, as you can see here. Now, there's an intermediate regime, which, as you can see from my schematic, might be positive or negative. And that actually depends on this prefactor here. You can convince yourself by looking at, what regime you're in by looking at small q. At small q, this term doesn't matter. The lowest order is just this term. And if the second derivative of the free energy density is negative, this negative sign will cancel with this one. The whole term becomes positive and you get an instability. Whereas if the second derivative is positive, this is negative and you're on this side. So we know that this part here is related to this regime, whereas this part has positive free energy density. Good. I'm drawing the whole thing. Well, I'm drawing it quadratically. No, it is quadratic here, yes. Oh, I know what you mean. Yeah. Sorry. I should have. Better? Thanks. I forgot to introduce, yeah. I had the figure in my notes on a different page and didn't copy it carefully. Thank you. Yeah, no, you're absolutely right. It needs to be quadratic. And also this is quadratic down. Well, I guess this is not too bad, but the other one was a bit. Thank you. Good. So what we learned here is that the second derivative, so the curvature of the free energy density as a function of the composition, tells you about whether homogeneous states are stable or not, without actually specifying what the free energy density is or anything like that. So if you look at the free energy density just generically, I gave you here the equation, but I think it's actually much more much better to draw something like that. I'm sure something like this has been shown last week. And if you want to look at the regions where, where the curvature flips, you need to worry about the inflection points, which are sitting somewhere here. And in between here, you have a region, first of all, the f prime. Well, I guess I don't need to. F prime is negative. So this is the region of instability, whereas outside for the simple forms like the Spory-Huggins free energy, it's positive. So this is the instability region. T, whereas it's stable outside on both sides. And this instability region is called binodal decomposition. Because what's happening is that if you start with a homogeneous system in this region, initially, because there will always be some fluctuations, you will get all modes that are within this length scale, meaning that have a length scale larger than 2 pi over this max of this root here. They will grow exponentially because it's an unstable system. Nothing to do with the fluctuation driven or anything like that. Really unstable. And there's a well-defined length scale which is associated with the maximum here. Let's call this Q max, which you can actually see in experiments. Like you prepare a system homogeneously, you then change an external parameter such that your free energy density becomes of this form, like for instance, lower temperature. And then if you are in this unstable regime, in this binodal regime, you can see this length scale. So that's the early time dynamics in the simplest case. You get something forming, and there's a well-defined length scale which doesn't depend on system size or anything, so you get many structures in a large system. Cool. Let's probably delete this. Any questions to this part? Because otherwise I would move to the late set. Yes. We're going to get to that. The question was whether we get phase separation outside the unstable region. And the answer, it depends, but I want to fill in the details. Any other question? Yes.
You mean that it comes out as like a correlation length or something like that? Or is that?
Yes, basically, I mean, so it depends on what order parameter you measure, but if in these simpler theories, the best order parameter is just the density itself, right? And you will basically see like high and low parts of the density field, which have this length scale, yes. So if you look at the spatial correlation or like G of R or anything like that, this will be the peak. Yes, sorry. Oh, can you repeat it? Why this is the one that comes up? What determines what the, oh, well, you can just, it's not so difficult to calculate. Actually, I think I do it in a, okay. So this is a biquadratic equation. You just maximize it. You treat Q squared as a variable like X or whatever, and then you maximize this, basically take the first derivative, set it to 0. And what you will find is that Q max is given by, let's say the square of this is given by minus F prime C naught over 2 cut. So all the things that are in here also determined, but it's not dependent on the mobility. Because again, the mobility just determines how quickly things happen, as you can see from this equation. Good. Any other questions? Let's move to the late stage. So as is often the case, it's easy to discuss the very early behavior and the very late behavior. In between, things are complicated. So I'm going to skip those, but I'm going to show you a simulation later. The keyword that we want to understand here is Ostwald ripening. Again, this will make sense once I told you a bit more details. All right. So I just told you that in some systems, we have initially some structures forming, like they grow exponentially. Eventually, this linearization that we did here breaks down, and the behavior is not described by this simple ansatz anymore. We actually need to go to the full equation, which has all these nonlinearities, right? You can imagine these logarithms being plugged in here and so on. Things are complicated. But what you learned last week is that exactly this kind of system possesses coexisting phases. Like a typical, maybe I can put this on this board, the typical concentration field. Let's have a system like this. A typical concentration field in the intermediate state would be one. We have multiple droplets like this. So this is the dense phase. and this is the dilute phase. So I typically call this inside and this outside. It's a bit arbitrary. And what I'm interested in is what's the equilibrium concentration in here, in this droplet? What's the concentration outside? No. Out. And then, of course, I'm also interested in where these droplets are and how large they are. So this is basically, if you want, a coarse graining on this field theoretic level, where I'm not describing the full concentration field anymore, but I'm looking at these objects, these droplets, and I just want to know how they evolve in time, which is a reduced description because my degrees of freedom are fewer, but it's a relevant description. I don't care so much about this small fluctuations in the concentration field anymore. So this is where I want to get. And this will also help us later when we discuss these chemically active droplets. Yes? Not quite, not quite. But this is what I'm going to talk about next. A bit more subtle. But this is exactly the next thing I want to discuss. Exactly. So the first thing we need to investigate is actually what's happening at this interface. Right? This is nothing you would get from a simple diffusion equation from what I actually raised from the board, because there are these strong concentration gradients that we have across the interface here would simply diffuse out. But again, you heard last week that in phase separation, this is not good. Yes. You have what? Because can you speak up? Oscillations. Oh, you're referring to the possibility of complex omegas? If you make the system more complicated, then you can have this, not from this. I mean, you see here that this is, I mean, and in all the systems I'm familiar with, the mobility is a real number, the free energy is a real number, this kappa is a real number, so this is all real. And then there's no way to get any oscillations. I'm sure you could study systems where they can, have complex mobility. I don't know what this means, but then you can get oscillations. You can also, if you have more species, this whole analysis becomes more complicated. You basically get a matrix equation here. What's relevant are the eigenvalues. And you might very well know that even the eigenvalues of a real matrix can be imaginary or complex. You can get oscillations from that. I think we discussed briefly Turing patterns this morning. In a general class of reaction diffusion equations, you can very well have oscillations. And this would also hold true for these phase separating systems. But you need more species. Good. All right, so I want to come back to this coexistence of the dense and the dilute phase. And I simply hope that well, Jacobs told you that the two conditions that govern this coexistence. One is that the chemical potential needs to be balanced between the two. Right, the chemical potential. I heard that this was a topic several times last week. So I think the chemical potential is really a central object here. It really tells you how the free energy of the system changes when you insert a particle. And since it's a field here, it tells you how the free energy of the system changes when you insert the particle at a certain position. This position dependent. And this condition then means that if you have a particle inside the dense, if you insert a particle inside the dense phase or inside the dilute phase, you would raise the free energy of the entire system by the same amount. Or put differently, if you transfer a particle from the dilute to the dense phase, you take out some energy, you put it in, it's the same amount, overall the free energy doesn't change. And that's, of course, what you want to be at a minimum. Hence, this condition. And the second condition is a pressure condition, which basically says that the pressure of the two phases needs to be the same. Now, this would be the full story if we would discuss thermodynamically large systems, like true equilibrium thermodynamics. However, especially in biology, we're often interested in finite systems. And that turns out to be a correction, which comes from surface energy. So let's call, just specify things a little bit. My droplets have radius r. And I hope Will Jacobs discussed this last week a little bit. So basically, you can think of the free energy of this system as comprised of the free energies of the individual phases, which are then given by the free energy density, like little f evaluated at these concentrations, plus a contribution from the interface. Each interface has a little surface tension, and you get a contribution to the total free energy, which is just a product of the surface tension times the surface area. And that's also the reason why these things become round, because this is simply the geometry which has the lowest surface area for a given volume. That's why I'm not even considering shape deformations, which are good. Yes.
I think one thing, another very you can.
I'm sitting somewhere in between, because you will. I mean, I'm certainly in a situation where the system has relaxed across the interface. So you can think of it as being relaxed on the length scale of the droplets, but it's not globally relaxed yet. And I want to discuss about the global relaxation. That's the aim. Yes, was another question. Good. Yes, I didn't tell you. The pressure in this case is simply given by C times U minus F, which is not transparent at all. But you can, if you want to convince yourself that this is the correct expression, what you need to do is you need to write the free energy of a system with constant temperature, constant volume. And then, I should have said it at the beginning, the concentration is nothing else but the particle number divided by the volume. And you know that the pressure is the derivative of the free energy with respect to volume. This is how you can get this expression. Minus. Yes. Yes. So, very good question. So there's some subtlety here when you have actually concentration variations. So both the chemical potential and the I see what I did here. Yes. I need to modify. So first of all, the chemical potential certainly has this this kappa term, but actually also this free energy density, I think, has the kappa term. I'm not 100% certain right now, but I think it does. So let me call this F int for the integrand. But I need to I'll double check.
Just the Gibbs free energy.
Yes.
Legendre transform of the Helmholtz.
Yes, if we want to. Yeah, if you want to think about this that way. Yeah. So we have an example here where the temperature and the particle number and the volume is concerned.
That's the original one. That's the little f. But here
that's the cap.
That's this guy.
Yes. I mean, this doesn't fall into this classical example because you have concentration variations like this.
But I mean, the pressure is Gibbs free energy per unit volume.
Yes.
So that guy, where you give chemical potential. Grand potential. Yeah. From grand potential.
Good. All are we clear? Yes. I mean, exactly. These things are easy if you discuss a homogeneous system, then everything is clear because everything is just governed by the total particle number. The extension to fields is a bit more subtle because, I mean, you already saw this in the chemical potential that you need to go to functional derivatives. And I don't remember fully off the top of my head how you derive the pressure, but I'm pretty sure it contains the gradient terms too. You have questions of you go from right to left, yes.
Okay. So in the picture that you drew, if the system has not relaxed in the global sense, why is the concentration? Like, what does the equilibrium mean here? Does it mean the common timing equilibrium on the free energy, or?
Yeah, we're gonna get there. I wanted to first, yes. Yes.
You've already here assumed phase separation of two homogeneous phases, and so you can define the pressure within each phase.
Thank you. So it's just, yeah, that's absolutely right. And just to repeat everything here, the comment was that this condition is not for the locally resolved pressure field, but it's actually the pressure condition across the phase boundary. So you have a pressure inside, you have a pressure outside, and there the gradient terms don't matter anyway. So you can get away with a homogeneous system. Thank you.
Like bubbles that have like radial distribution that depends on the lowest nodes?
Okay, the question is about the initial size distribution of these droplets, basically after spiral decomposition. It's absolutely correct that it depends on the details, especially like how you set up the initial mode, and there will be a distribution. I have never studied this, so there will be a distribution. I don't know what it looks like. But what I will tell you well, I still have some time. What I will tell you in a bit is what the distribution of a while looks like. That has universal behavior. Good, this is good. More questions? Okay, let's keep on going. Okay, so we have this coexistence condition. The chemical potentials, this is what I would call a chemical equilibrium. You can just move particles in and out. This is what I would call a mechanical equilibrium. The pressure here, you actually need to think of an osmotic pressure of the solvent. So this basically pertains to moving solvent particles in and out, if you want. Good. Now, one can, of course, insert expressions for the chemical potential, which we just discussed how to compute. You can do the same for the pressure. One gets two sets of nonlinear equations, and one has two unknowns. And one can, in principle, solve this. But since these are nonlinear equations, it's actually very difficult. But numerically, one sometimes needs to do this, of course. What I think is more helpful is actually a graphical interpretation of how one can solve this. And I'm going to do this by repeating this plot that I had for the spinodal decomposition. Let's say I have some free energy density. I have, again, a double well potential because I want to have phase separation. Otherwise, nothing happens. Now I want to discuss two cases. First, the simple case without this surface tension, which is basically macroscopic phase separation. And then you can convince yourself that these two equations describe basically a graphical condition, a geometric condition, where you need to have a common tangent. Well, if I were able to draw better, then this would be a tangent. Like so. And the solution to these equations would be the points where this tangent touches the free energy. And the reason that this is the graphical interpretation, so just maybe to convince you this would be the concentration inside, that's the higher value, right? And this, this would be one outside. To convince you that this is actually the correct expression, but first of all, you can look at the chemical potentials. The chemical potentials are basically nothing but F prime. Let's forget about the kappa term because we have homogeneous phases. The F prime, this is really just the slope of this. And what this is saying is that the slope at these 2 points must be equal, surely fulfilled by this tangent. The pressure, yeah, so it's basically, maybe it helps actually if I write it out. Minus mu, no, F. This is what we had there. Again, no gradient terms. I'm just writing mu because we know that the chemical potential must be the same anyway. So I have the same on both sides. And we don't have any surface tension at this point. And this is just an equation for a linear function, if you look closely. So this is the slope. So basically, if you want to rearrange this, you have here FC equilibrium C out, out minus FC equilibrium in. This is just this difference. Yeah, if you want to see that. And that is given by the slope times this difference. C equilibrium out, C equilibrium in. So I think that is at least illustrative that the solutions of these two conditions are this common tension. So you can really just read it off. And then if you now go back and say that I have a free energy density which actually doesn't have this double well structure, just like a single well, which would be a system which is dominated by entropy, then the only common tension I can make is one which touches the free energy at one point, which implies that all phases need to have the same composition, which is a homogeneous system. So you can't have phase separation. So in order to have phase separation, you can immediately see that you need to have this structure. Good. Now, the second part I want to do, some other color. What happens if I actually have surface tension? All that's happening is that I have a correction here. And graphically, this means that I still need the same slope. But I now get an extra offset. Maybe I can show it. Which is exactly equal to this term, which is, by the way, called Laplace pressure. Should have said this. The extra pressure generated by surface tension. And so the linear equation is just modified by this term. And then if you look closely, you see that the coexisting compositions move to the right a little bit. So blue is the case with surface tension. Red is the one without. Yes.
Already asked this. Elaborate more on why the pressure takes that form.
So I would, you have to go through the system. The calculation is not so complicated. You define the total free energy of the system as F times. Just consider a homogeneous system with n particles, volume V, and now you just define the pressure like normally as constant n. And now you just have to, you just need to do the derivative. It's not so easy because Z, right? You just take this derivative, you basically get F prime of n over V times the internal. Times basically C. And then minus F. I'm not sure I'm doing this calculation automatically correctly and above, but this is all you need to do. You need to calculate this derivative correctly. This might or might not be correct. Yes. Good. Any other questions? Good. Let's move on. Okay, so what I showed here graphically is that if I have surface tension, if I have Laplace pressure, then my coexistence concentrations move up a little bit. And one can actually calculate this also in a bit more detail. And one basically finds, well, what one can do is one can first calculate the coexisting concentrations without Laplace pressure. This is typically what I denote by C out not for no Laplace pressure. And I can then consider this term as a perturbation, like basically assume that this term is small and ask how these solutions actually vary or deviate from the solution without this Laplace pressure. And without giving you the full derivation, I basically get blue. I think this makes sense. I get that this is basically given by the unperturbed case times an exponential of this pressure difference, the Laplace pressure, times C naught times KBT. This is not immediately obviously right now, and this is an approximation. But what is probably more useful is one can approximate this further, and this would be sufficient for our purposes, and expand this whole term to linear order and 1 over R, basically for large droplets. And one simply finds that there's a correction to the order of 1 over R, not surprisingly. There's another length scale here, just to make this dimensionally correct. And this length is sometimes called the capillary length. And it's simply given by 2 gamma over Cn not KBT. Details don't matter too much, but this is often on molecular lengths. So like some molecular lengths. So you can see that if I have droplets that are large enough, then this will be a small correction. And I don't need to worry about the higher order terms. What you can also see immediately is same that we saw graphically here, that because this is a positive quantity, and the radius is of course positive, surface tension will always increase the concentration again, and it will increase it more for smaller droplets, because smaller droplets have smaller R, so this term has a larger contribution. And this is critical. This is really where I want to get at. But basically, I can illustrate it here, I think. Just switch back colors. Let me draw down another schematic. So this one's quite full. So again, I have the situation of a full system, volume V. And let's just consider two droplets, one large one, one small one, R1 and R2. What we just calculated and convinced ourselves graphically of is that, well, we can determine these coexistence conditions. We can determine the concentration inside this droplet, inside this droplet. This turns out to be not the most important thing. What is more interesting is actually the concentration outside these droplets. And what I just told you at length is that there is a gradient here, meaning that the concentration outside the smaller droplets is actually higher as compared to the concentration outside the larger droplet. This is simply due to either this equation or this graphical construction. Another way of thinking about this is that, well, I'll bring this argument later. Anyway, what we see here is that there's a higher concentration right outside this droplet as compared to this. So there's a concentration gradient, and concentration gradients in this dilute phase give rise to diffusive fluxes. So the dilute phase can be easily approximated, it can be well approximated as an ideal solution, meaning that we can use our intuition from the ideal diffusion equation, where diffusive fluxes are driven by gradient and composition. This is what's acting here. And we get a material transfer from the small to the large droplet. Yes?
Possible to gauge why the equilibrium concentration is higher outside of smaller droplets?
I will try to give you some. Whether it works or not, you will have to judge yourself. I'm almost there. Yes, any other questions? Yes.
Like what sets this ratio between C in and C out?
C in and C out, it's basically, I mean, you can see it from here. It's mostly determined by these minima, right? Yeah, exactly. And one can, I mean, I try to be quite general here with free energy. One can actually do very good approximations when one takes a concrete form. So it depends on, well, mostly this parameter. Yes.
Yes, you also get the top. If you think of grand free energy.
Yes, one can do this, yes.
Then it's much simpler condition. It's just the two minimums are equal. That's just the pressure. And you're at the minimum.
Yes, we will go there tomorrow. The issue is that you then can't have coexistence. You can't have two phases of different composition in the same system, because you're exploring. We can discuss it. I don't want to sidetrack too much, but yes. Well, okay, so this is a qualitative argument at this point. How fast this project, this dynamics work, it depends on the details and the mobilities and so on. Yes, definitely. And also the distance, of course, and I'm not doing this. Yes.
But if you really have flux, get out.
Sure. No, what's happening here, first of all, let me finish the argument. What's happening is we have a material transfer from the small to the large droplet. And so you're absolutely right. If you have diffusive transport, in principle, we need to refill what's being removed here. And this will actually happen by transferring molecule from the droplet to the dilute phase, because we have a fast equilibration across the interface, which I'm not describing in detail, but this ensures that locally, right outside the droplet, this condition always holds, because this equilibration across the interface is extremely fast compared to these long length scale diffusive fluxes. No, it will shrink because it loses material. Yes, absolutely right. So what will happen, exactly. So what will happen is that small droplets shrink, large droplets grow, and one can actually be quite quantitative of what large and small means. And I think I still have enough time to go through this. I'm going through this in detail because we will do very similar calculations once we added chemical reactions. And that's why I want to really make the arguments very clear. So let's explicitly ask how a droplet, any given droplet, changes its size given by its volume. I'm thinking about a 3D system, but one can do the same calculations in 2D or any dimension. Such a droplet changes its volume basically proportional to how much flux integrated of the entire surface goes away from the droplet. So like, okay, the J out is the flux away from the droplet, so that the volume, if that is positive, then the volume shrinks. And there's a normalizing denominator which looks like this, but it's not super important at this point. In the simple situation where these droplets are far apart from each other, they will all feel a common concentration in dilute phase. They don't interact directly with each other, but they basically all feel a common concentration, which are typically calls the infinity, to emphasize that it's far away from the droplets. And in that situation, one can approximate this flux like so. This is in 3D. In 2D, this equation looks a bit more complicated. That's why I'm doing it 3D. And to derive this equation is part of the assignment. So I'm not going to do the derivation here. But one can plug this in here and find that we basically have, I mean, these are just prefactors that are collected. And what's important in the end is the difference of the concentration right outside the droplet and the concentration far away. If right outside the if the concentration right outside the droplet is larger than the concentration far away, we get a positive efflux. So the droplet will shrink, not surprisingly. And this we can now express, equilibrium concentration we can express with this approximation, which is important because it allows us to also capture the effect of surface tension. So you have this equation, and if you collect terms a little bit, you find that this is d over r times capital delta, which is what I would call the supersaturation. Okay, and a factor alpha. And these are just abbreviations I introduced for simplifying things a little bit. I give them here. These are, so alpha is a constant which basically captures the effect or the strength of surface tension. Just in value, it's a length, doesn't matter too much. And delta is dependent on time because the concentration far away might depend on time. And so the delta is just a normalized concentration. I think it's the simplest way to think about it. If you look at this equation, I hope one can see this in the back still. What's important to us is not really the details, but whether droplets shrink or grow. We just need to look at the sign of this bracket here. And what we basically can identify is that there's a critical radius, RC, which is, or which you can calculate from here. And if we plug in, well, let me do this actually correctly. So this is alpha over delta. That makes sense. And then this can be brought in. So what I calculate here is a critical radius, and all the droplets that are above this critical radius will grow, and all the droplets that are below this critical radius will shrink. So that tells you that this whole story that we basically made up here for just two droplets holds it more generally. All these droplets talk to each other via the dilute phase, via the C infinity. And you will lose droplets over time. And one can now actually calculate C infinity from material conservation. So we're still in a situation where we don't have any chemical reaction. The total amount of material is conserved. So if we know the size of these droplets and we know the concentration inside, we know how much material is in droplets, and all the rest must be in the dilute phase. So if we, like, I'm not going to go through the calculation, but maybe here. So the idea is that we I have a collection of droplets. Let's describe it as a continuous probability distribution. Like we're going to a really large system with very many droplets. We have a distribution of droplet sizes. From that, we can calculate C infinity, which might depend on time. And this distribution might also depend on time. And what one can show, and it's a lengthy calculation, I'm not going to reproduce it here. One can show that actually this critical radius self-adjusts so that it's equal to the mean radius, which means that if a small droplet disappears, all of a sudden the mean radius is going to go up because this droplet is not there. It's not going to count to the mean anymore. And it shows that this mean radius is increasing. But since the mean radius is equal to the critical radius, it means that all of a sudden there are now droplets which are below the critical radius and start shrinking. So what you get is basically a cascade where the average droplet size increases in time. But there's always a collection of droplets that are shrinking and some that are growing. And this is really a process where you get fewer and fewer droplets over time. They get larger and larger on average. So that's a coarsening process that we call phosphorypening. I'm just going to put this here. And what's remarkable is that under this assumption that the droplets are far apart from each other so that they don't have any direct interaction, there's no direct correlations, which might mess things up. So where they only interact by exchanging material with this common dilute phase, you can actually calculate the time course of this mean droplet or critical droplet radius. And you can even calculate analytically this size distribution, which turns out to be universal. This is probably the point where I move back to slides, if I can. Would it be possible to turn off the lights in the middle again? Somebody, I'm sure, would hit it wrong. Just for contrast. Okay, perfect. So I promised you, first of all, the video. So I went through lengthy calculations to show you the early stage dynamics of these droplets, like what is known as spinal composition. And I also try to convince you that in the late stage, we have this coarsening process. So I told you very early when we derived this equation that one can simply put it in the computer, and that's what I did here. Now I do it in 2D because it's much easier to visualize. I start with a homogeneous state. And you might see a little bit of noise. So I put some initial disturbance. And that's simply to basically enact or enable this initial instability. When I play the movie, if it plays, droplets appear. And you see there's a certain length scale that comes up, and that's exactly this Q max that we were talking about earlier. And you probably also saw, maybe I can stop it. I can't. Why can't I? You probably saw that there's a size distribution on these droplets quite early already. The question was asked earlier, but the details really depend on how your particular system is on. And now that the simulation is running a bit longer, you see exactly this offset ripening at play. When you look at it, all the small droplets disappear, all the large droplets grow. And without quantifying it here in detail, I think you can convince yourself that the mean droplet radius is increasing. And this is exactly what I tried to explain here. No, actually, I should say that in this simulation, we are not in the regime where we can assume these droplets to be completely isolated. I mean, you see that many of these droplets are quite small, quite close to each other. But the general behavior will still be there. And the reason for this general behavior is extremely fundamental because in the end, this is still a passive system. We are not yet in this lecture going to an active system. So this whole system is just trying to minimize its free energy. Now, it can't do very much because, I mean, it's already equilibrated across the interface. So that part of the free energy minimization is already done. All it can do, basically, is to minimize out of a long length scale, or, put differently, it can reduce the overall interfacial area. That's exactly what's happening here, right? Because you can imagine if you have multiple small droplets, you have much more interfacial area as if you were to put all this material into one large droplet. That's simply the volume to surface ratio scaling that you have in these systems. Now the movie stopped because I didn't want to simulate it any longer, but in principle, this process would continue until you have exactly one droplet. And if all the material wants to basically combine in one droplet, that's the final state. And that's why, and so this overall the decrease of free energy is really the driving factor here. So that's why it doesn't depend on the details. And the kinetics that I went through here are then just for quantitative comparison. But the process will always be that these phase separating systems want to collect all the material in one large phase. And the surface tension that we introduced by this kappa term over there is unavoidable. It comes really from phase separation, as you heard last week. I want to tell you a little bit more detail about this Oxford ripening. In particular, if you go through the calculations, which are collected historically, they have been done by Lifshitz and Sliosov, and at the same time by Wagner. Now, this paper is much less known, presumably because it's written in German, and nobody can really read it. If you are able to read German, which is probably the vast minority here, this paper is much easier to understand, actually. This is extremely difficult to go through, but this theory is also discussed in books and so on. So you can do a scaling theory for this size distribution, and there are two interesting results. One is that the mean droplet radius, which again is equal to the critical radius, scales as t to the 1/3. It's a very stable result that we can also find experimentally. That's the seminal Lifshitz-Sliosov-Wagner scaling. There's also prefactors, like, of course, it scales with the diffusivity because that's the only kinetic process we have. That's not so interesting, right? And if you have stronger surface tension, which gives rise to larger capillary lengths, then it's also going to be a stronger process. But it's t to the 1/3 scaling, I think, is really interesting because it shows that these systems evolve slower and slower over time. And the other interesting result I already mentioned earlier is that the size distribution I was mentioning here, which is also shown graphically here, becomes universal after some time. I mean, of course, there's an initial transient, but it becomes universal in the sense that there's actually analytical formula for the normalized droplet radius. So rho here is just the actual droplet radius normalized to the critical size. It has this horrible expression, but when you plot it, it just has a very peak distribution. Interestingly, there's a maximal size, which is 3/2 of the critical size. And you see that basically all the droplets that are above here, about half of them will grow, whereas all the other ones shrink. This is really the Oxford factor. Good, yes, question. Not intuitive, I'm afraid. No, not. I don't have any intuitive understanding for equations like this, and it just comes out and you plot it and it makes sense, but no. But what's important, yes, what's important is that really the critical radius is what is governed by the mean radius. So the mean and the critical radius, this is also not apparent, but you can calculate it. You basically find that the mean of this horrible distribution is 1. There was a question over here.
Seems like it's very right for droplets.
Each individual droplet is supposed to be spherical, yes. Fair enough, yes. You can do more involved calculations, particularly if you have two droplets. With two droplets in 3D, you can use bispherical coordinates. I don't know if you are familiar with those, but these are orthogonal coordinate systems which allow you to solve the Laplace equation, which governs diffusion between those. And you can get more exact or more correct, like improved equations for the flux between the droplets, which basically hold also when you move the droplets closer together. So you get correction terms, but it is doable. I wouldn't advise you to do that. It's a bit more complicated. But in the end, you just get small corrections to the kinetics because the whole process is still governed by this thermodynamic principle. So, yes, true. If you have to worry about fluctuations, initially, yes, definitely. If you're on the late stage, I would assume not really, because everything is large, like all phases are large, and you're just worried about the large scale transport. I don't think this is. Yes, second row. That's a very interesting. The question is about the time scale of transitioning from the early to the late stage dynamics. It's a very interesting question. I'm afraid I don't have a good answer, but there's a time scale associated with the instability. That would be my first guess, but I don't know. Should we? Yes.
I missed this universal size distribution. I mean, it's coarsening, so what is it?
So it's describing the normalized droplet size. So you normalize you look at the distribution of all droplets, measure the radii, normalize it by the mean radius, and this distribution has a universal form. And the mean is exactly, this is a peculiar part of this system, that the mean is exactly equal to the critical radius. The critical radius decides which droplets are growing and which ones are shrinking.
But is that decided, you know, is this distribution decided by the initial range of Qs?
No, it's the initial phase, there's an initial transient, which depends on how you initialize the system. But if you let the system run on for long enough, it will always converge to this distribution. The assumption, of course, that you have an infinitely large system. If it's eventually in a finite system, it's limited by system size, obviously.
Another question. If you assume you're in a spinoidal decomposition, but if you have thermal fluctuations, you could be locally stable.
Very good point. This is something I wanted to mention. I'm running out of time, but yeah. Maybe just very briefly, just where are we? Here. Okay, this is a plot of a phase diagram where we just have the interaction parameter from this Flory-Huggins energy here. So higher interaction means stronger phase separation. Here's the average composition of the system. So the free energy density has a second derivative which is positive in here. So that's the spinodal region. If I prepare a system in here, I will have this instability. If I'm outside this blue line, which comes from this calculation, then I can't have phase separation. In between, the homogeneous state is actually stable, but I can still have phase separation. And phase separation is actually the state of lower free energy. So here I have nucleation phenomena. If I have noise, then I nucleate droplets and so on. It's a bit more complicated. We don't need it for the lecture, so I skip it. But thanks for reminding me on this. There's so many questions. I don't know how we deal with questions and running over time. Okay, Marcus. Yes. Right. That's correct. Okay, no, this is interesting. So first of all, it's actually correct. If you are closer to equal composition, you don't get droplets, but the energy configuration which minimizes the surface area are stripe-like or labyrinth-like patterns. Now, typically, if you have spinodal decomposition there, you get curved stripes. So you still have curvature, and these effects still kick in. You still get, so basically, this two over R is just the mean radius, mean curvature, and this will still kick in. If you have horizontal stripes, which is also possible, you're basically effectively in a 1D system, and coarsening in a 1D system is different. I should say that this universal coarsening with the T to the 1/3 holds in dimension 2 and higher. In 1D, you get much, much lower coarsening logarithmically with time. So you still get coarsening, but it's slower. Question over there.
One third is still applied. You have the position with 1/2.
Yes, it does. Yes, it does. Unless you're in this 1D case, which we just discussed. But if you have curvature, then this is still what's happening. Yes.
The slide.
Yes, I can find it again. Yes.
Plot C, like the most frequent droplet size is not RC, it's a little bit above RC.
That's correct.
So there's like two different length scales in the system. What's setting the maximum droplet frequency size?
I mean, I'm not sure if I would call this two different length scales. I mean, there's a continuum of length scales, right? And you can characterize this distribution either by its maximum, either by this point or by the maximum or by the mean. They all scale with constant fractions. So it doesn't really matter which one you take as your characteristic length scale. I don't know exactly what governs this maximum. I mean, I guess you can calculate it from the analytical form, but I don't think there's much insight in there. Because in the end, it's a broad distribution. We might want to stop here, and then, but I'm around until Friday. Also, there are 2 more lectures.